Nowadays, various next-generation energy sources are being discussed. The energy of the future must be ecologically friendly, clean, and safe. What we need is a reliable energy source that can sustain our daily lives and our industry as well. Determined to make these dream energy sources a reality, Professor Yoneyoshi Kitagawa, here at the Graduate School for the Creation of New Photonic Industry, teamed with the Hamamatsu Photonics and Toyota Motor Corporation, have been developing a compact laser fusion experimental reactor called CANDY. Fusion is a nuclear reaction that naturally occurs within the matter at the sun's core, releasing an enormous amount of energy. Under the common conditions, atomic nuclei repel each other. But in extremely high temperatures, comparable to that of the sun, lightweight atoms like hydrogen turn to plasma and their nuclei fuse together. This process gives you a birth to an immense amount of energy. Our research team, headed by Professor Kitagawa, is using laser technology to artificially reproduce the conditions that induce nuclear fusion. Scientists overseas, such as in the United States, are researching laser fusion methods using large-scale specialized facilities. On the other hand, Professor Kitagawa's team is independently striving to develop an original compact device that will make nuclear fusion energy available sooner.
ターゲットを繰り返し投入すること、それからレーザーをいかに効率よくそこに照射することができるかで、最後はそれから核反応で出てきた、中性子なりガンマ線のエネルギーをいかに取り出して発電に持っていくか、全てが同じような未成熟な状態ですので、バランスよく開発していかないと、核融合というものに到達しないであろうし、発電をするための近道であろうと思います。で、それが我々のスタンスです。
Recently developed high-power semiconductor laser technology may be the key to realizing this dream. The high-power laser beam emitted by the semiconductor is divided into two symmetric counterbeams that simultaneously illuminate the hydrogen fuel pellet. Then high-repetition rate laser beams irradiate the hydrogen fuel, causing it to implode and ignite and inducing fusion reaction. This technique is known as the fast ignition scheme fusion. Professor Kitagawa's team, together with researchers from Osaka University, made great progress toward achieving these conditions for nuclear fusion by successfully producing temperatures of 20 million degrees Celsius, higher than the sun's temperature. But producing single fusion reactions is not enough. These results can only be applied in practice if the fusion reaction is inducing repeatedly. To achieve this, our researchers have developed repetitive pellet injection and irradiation system. We have successfully achieved the repetitive implosion ignition of fuel pellets fixed on a desk. In our latest experiments, fuel pellets with a diameter of 1 millimeter are repeatedly injected inside of the vacuum chamber and irradiated by laser beams with great precision. These images capture the very moment when the 1 millimeter diameter pellets in free fall is irradiated by laser beams, inducing fusion reactions and emitting bright light. This new technology, when perfected, may bring us one step closer to the implementation of repeated implosive fusion. But how can we extract the energy produced during these high-rate repeated fusion reactions in the future? The inner wall of the reactor is lined by so-called blanket, a liquid metal mixture meant to capture the heat released during atomic fusion. The liquid metal circulates and carries the heat outside the reactor, producing steam and setting a power generation in motion. This is the concept behind CANDY, the compact laser fusion experimental reactor.
それがキロジュールレーザークラスの装置なんですが、その後100キロジュールクラスまで上げまして、投入レーザーエネルギーと同じ程度の出力を目指します。
The development of the CANDY reactor is in full progress in a challenge to bring fusion energy to the world as soon as possible.